Okay, great. Without further ado, it's a great pleasure to have Mike Shulman here at the CMU HoTT seminar. Thank you, Mike, for agreeing to share these thoughts and this work with us here in the HoTT seminar. We've been eager to learn about your latest project. Let me just take a moment to thank you also for all of your contributions. You've been a great leader in the field of homotopy type theory right from the start. You've made countless contributions, both fundamental mathematical ones and also others in support of the community. I'd like to thank you for all the work you've done, all the work you've put into the subject and into the community, much of it without taking or receiving any credit at all. Mike, by the way, is that anonymous referee who fixed your paper rather than simply rejecting it. I think the great attendance today can be seen as an expression of our gratitude and appreciation for all of your contributions, Mike. And of course, for interest in the topic of today's talk. So I'll turn it over to you, Mike.
Thank you very much for those kind words, Steve. I really appreciate it, and I love this community, and I'm happy to be able to contribute to it in all the ways that I can. This is sort of an exciting talk for me to give because it's sort of something that I have wished for a long time, and I've sort of been quietly dissatisfied with the state of things for a long time, but I haven't really had any concrete alternatives to suggest, and so I haven't really been able to speak up about my dissatisfaction and feel honest about it. But now I finally have, Thorsten and Ambrose have been a big help, I mean, in some sense, these ideas were theirs originally, and then I sort of picked them up later, and we've finally come up with something, or pretty close to something, that I think I believe is going to work. So there are a few sort of holes here and there that aren't completely filled in, unfortunately, but I think the general picture is emerging quite clearly and quite beautifully, and I'd like to share that with everyone here in these three talks. So I've called this talk towards third generation HoTT, and that's a little bit presumptuous, perhaps, because it suggests that the first and second generations are to be superseded by the third generation, which isn't necessarily true. But really all that I mean is that it's a third way of doing homotopy type theory. So let me sort of first review the first two ways and some of their advantages and disadvantages. So the first generation, I guess what I'm calling it, is what nowadays we often call Book HoTT, which was the original homotopical viewpoint on Martin-Left type theory, which was used by Audi and Warren and Blavatsky and others in the early days, and was used in the HoTT book, which is where we get its name. It's based on intentional Martin-Left type theory, where the identity types are characterized by this identity elimination or path induction, and we assert univalence as an axiom to make it homotopical. And this is nice because it's easy to do in sort of old style proof assistants like Coq and unmodified AGDA. You just assume univalence as an axiom, and there you go. Now we know that it has models in higher toposes. But from the beginning, it was clear that there were disadvantages to this, in particular that it's not computational the way type theorists like a type theory to be, because the univalence as an axiom is sort of a stuck axiom. You can't compute with it, and so you have non-canonical terms belonging to the natural numbers or something that you can't actually evaluate. And another disadvantage that's related to this is that there are a lot of laws you would like to hold that are not definitional laws. So for instance, you'd like to say that two pairs are equal precisely when their components are equal, and that's true up to equivalence in Book HoTT, but it's not true in any sort of stronger sense. And similarly for functoriality laws and so on and so forth. So the second generation solves some of these problems. There are various different cubical type theories now, due to a lot of people here whose names I'm not going to read them all out. The basic idea of cubical type theory is that instead of equality or identity types being defined inductively, as in Martin-Left type theory, we have path types that are defined using maps out of an interval I, which is sort of not an ordinary type, it's some kind of a pre-type or exotype. And then to get the homotopy theory, we have the con operations, which are basically saying if I have sort of part of a cube, then I can fill the rest of that cube in all dimensions. And we assert those explicitly in the syntax and give computational rules for them. And then we can prove univalence because we add in these extra type formers called glue types. And this satisfies canonicity, and recently John and Carla show that it satisfies normalization too. So it's a computational theory. So it solves that problem with Book HoTT, and it also solves some of these problems of definitional equalities. A lot of these become functoriality laws and so on that we'd like to now hold definitionally, or at least in a stronger, to a stronger sort of isomorphism. It does require a new kind of implementation, but it has now been implemented in Cubical Agda and RedTT and CoolTT and various other experimental proof assistant type things. So it solves a lot of the problems with Book HoTT, but I've always been a little bit dissatisfied with it. I've never really complained very loudly because, as I said, I didn't have an alternative to suggest. So, but now now that I do, let me say why I'm dissatisfied with cubical type theory. So one reason one might be dissatisfied with it is that it's not yet known to have models in higher toposes. But I think that's sort of just a matter of time. We know that we have models of cubical type theory in a model category for ordinary topological, for ordinary spaces. Simplicial sets or topological spaces is equivalent to that, and we should probably be able to use similar techniques for other higher categories as well. It just really hasn't been done yet. So what is it to not like about cubical type theories? Well, one of my problems is just philosophical. One of the things I really liked about Book HoTT is that the identity elimination rule, you can argue it to be conceptually fundamental to the notion of equality. Basically, it says it's basically sort of a substitution of equals for equals in some sort of fancier sense, or like the Leibniz, whatever you want to call it. Once you have this simple rule, then you automatically get all the higher homotopical structure. So you can present as a slogan that homotopy theory is really implicitly present in the foundations of mathematics, even if you didn't put it in by hand. And this is a nice story to tell to philosophers, and it's sort of accessible to students to a certain degree. Whereas in cubical type theory, identity equality is sort of defined using a homotopy theoretic idea of paths. And it's sort of, the motivation for that basically comes from homotopy theory, and you put in the higher dimensional structure by hand using the con operations. And that's fine if what you already know that you want to do homotopy theory, right? So you're essentially explicitly writing down a type theory for homotopy theory, but it doesn't have the same philosophical import. It's basically saying we have homotopy theory there because we put it in because we wanted it. And I think it's not as accessible to students if they don't already know some homotopy theory. So that's sort of one thing that I would like to be able to improve, I guess. Another sort of circle of disadvantages have to do with the interval. I'm a little bit on more shaky ground here complaining about this, because I've never actually tried to implement a cubical type theory myself. But the impression I get is that having the interval around complicates the meta theory. It's harder to explain, it's harder to implement. You have to deal with how to termination check the boundaries. When I see people doing things with Cubical Agda, and I try to do something with it myself, it's tricky to display the boundaries to the user in a useful way. People tell me it's hard to implement higher order unification. Clearly, there's a lot of progress left to be made. Right? So I'm not saying like cubical type theory is fundamentally impossible or difficult to implement in any of these ways, but because it's difficult, maybe that's a reason to be interested in exploring alternative approaches as well, also, in addition to cubical type theories. And finally, there's a problem which is shared by both Book HoTT and cubical type theories, which has to do with these characterizations that I mentioned before. So there are a lot of characterizations of identity types that you can find in chapter 2 of the book. So like I mentioned before, that the identity between two pairs is a pair of equalities. An identity between functions is given by function extensionality. And identity in the universe is given by equivalences, that's univalence. But in Book HoTT, all of these are only equivalences, not equalities or isomorphisms or anything like that. So you pass back and forth, you have to transport across some equality. In cubical type theory, a lot of these equivalences become definitional isomorphisms. So by definitional isomorphism, I mean you have a map in one direction and a map in the other direction, and then the composites are definitionally equal to the two identities. So this is stronger than an internally expressed equivalence, where you would only have equality types here for the instead of for the composites, but it's not as strong as a definitional equality. You still have two different types, but so that's really very useful, much more useful than an equivalence. But unfortunately, this characterization for the universe is still only an equivalence in cubical, even in cubical type theory, because we prove univalence from these glue types rather than sort of getting it directly from the characterization of paths the same way we do for these other ones. So this is a certain kind of limitation on the usability of univalence, because if we have an equivalence and we make it into an equality in the universe, we pass it through univalence, and then we extract out an equivalence from that, we don't get back the same underlying functions that we started from, even up to definitionally. We only get them up to homotopy, up to a typal equality. So maybe this is a big problem, maybe it's only a small problem, maybe you can avoid it. But I think it's still something that's worth trying to improve. So what I'm going to describe is work in progress, which is close to completion, I would say, towards a theory that we call higher observational type theory. And the reason for that name will hopefully become clear, especially if you know what ordinary observational type theory is. The abbreviation for this name is I don't know whether it's fortunate or unfortunate, but there it is. This theory does have models in higher toposes, including spaces. It has univalence essentially by definition, and I'll explain later what I mean by that. Maybe not quite exactly what you might think it means. It shares this nice property of Book HoTT that homotopy theory is emergent rather than explicit. So although the rules, I believe, at least have a convincing philosophical explanation, even if you really didn't believe in higher homotopy to begin with, or you weren't setting out to do higher homotopy. And we haven't proven that it's computational, and we haven't even fully completely finished writing down the theory yet. But I think it's reasonable, and I think Thorsten and Ambros agree that it's very reasonable to hope that it's going to be computational. There are no obvious stuck terms the way there are in Book HoTT. Sort of everything that we've been able to write down, we can sort of see how it should compute. So the plan for these 3 talks is today I'm going to talk about the basic syntax of this theory. And my goal is to convince you that it feels natural and is nice to work with. And I'll leave out 1 or 2 things, which I'll then finish up next week. And those last few things will then push us in the direction of understanding some semantics of the theory, which turns out to match very nicely with the semi-Cartesian cube category. And then on the last week, I will say something about building univalent universes in semantics. I probably won't be able to do into all the details, but hopefully we'll get the basic idea. Okay. So as Steve said at the beginning, let me reemphasize this, right? So if you have questions during the talk, please chat them to Steve, and he'll answer them. I don't want somebody to be lost partway through and then lose all the rest of it, right? If there's something that can be clarified right away, please ask it. So let's start by talking about equality. So Eric Bishop, in one of his book on constructive mathematics, he wrote that he thought a set should be defined by describing what exactly must be done to construct an element of the set and what must be done in order to show that 2 elements are equal. So this is a little bit different from the way we think of a set in ZFC or something like that, but as it includes equality. In ZFC, we incorporate equalities as we need to by constructing like equivalence relations and taking quotients and so on and so forth. But it's very convenient to take this perspective in a type theory where we sort of separately specify the elements of a type and then also the notion of equality for that type. And of course, there's more than one kind of equality. There's definitional equality, and then there's sort of typal or propositional equality. And in ordinary Martin-Love type theory, we're already following this principle for definitional equality. If you consider types that have eta rules, so for instance, for the product type, we have a rule for constructing an element of the type, exactly what must be done to construct an element of the set or the type. And then we have a rule for proving that 2 of these things are equal by checking that their components are equal. This is the eta rule. And then, of course, we have other rules, the elimination rules and beta rules that are determined by sort of harmony with these rules. Now, you might think, well, can we do the same thing for the propositional equality type, or the typal equality? And this was done by Alton McBride in ordinary or lower observational type theory. So what they did was they said we have this equality type that applies to any type, but instead of being defined inductively the way Martin Luff the identity types are, we're going to have constructors of this type that correspond to that are defined in terms of the underlying type former that we're talking about, right? So in order to construct an equality in the type of pairs, we have to give a couple of pairs of equalities between the components and then pair them up. So this is sort of a special pairing up equalities constructor. The comma with the equal sign over it is a pairing constructor for equalities. And they did this for all the different kinds of type formers and came up with a pretty nice type theory. But the problem with this type theory is that it's non-univalent by construction. So in order to deal with equalities of equalities types, they essentially postulated proof irrelevance, that any two equalities are equal in the same type or equal to each other. So this is sort of the reason for calling what we're doing higher observational type theory. We'd like to have some version of this, something like this, which is univalent, which allows non-trivial higher equalities. Before we go on, let me lay some rules about notation and terminology. So for lower observational type theory, I was talking about equality types and writing them as EQ. In the univalent context, I'm going to talk about identity types and write them as ID. And I'm going to call their elements identifications. Here's the rule for the formation of these. And because I want to emphasize exactly when I'm talking about a rule of the type theory that I'm describing, I'm going to put green highlights around the rules of this theory. I'm going to simplify things by omitting these sort of unchanged ambient contexts, sort of gamma that you would some people would usually put in front of these things, and you can think of that as a sort of meaning we're working in some logical framework or something like that, where there's sort of an ambient context in all situations. So under these conventions, how do we treat these identity types? So in ordinary lower observational type theory, this rule for pairing up equalities in a product type says that the equality type of the pair type behaves like the product of the equality types of the component types. And if we were going to do the same thing in higher homotopy theory, then we would need a rule for the identity type of a product type, and we would want to say that that behaves like id A cross id B, and then so on for id and id and so on and so on. Now we could do that, but it's easier to actually make it a computation rule so that the identity type of A cross B is actually definitionally equal to the product of the two identity types of A and B. And then if we want to apply this to id of A cross B, we just apply this same rule twice. First we compute in the subscript, and then we compute on that product in the subscript to get id A cross id B. Okay, so this is sort of the basic idea of how we compute with identity types for, and we're going to have rules like this for every type former. I'll come back to some of the other type formers later, but for now, the non-dependent product type will serve as a good enough example. So now, so that's how we deal with types and identity types. What do we do with terms? So Bishop, we can go back to Bishop again and look at his definition of a function. So he talked about an operation, which is a way of making elements of one set into elements of another set. But then he said an operation is only a function if it preserves equality. If whenever we have two elements of the input and that are equal, then the elements of the output are also equal. And this is implemented in Martin Luff type theory, ordinary determinant type theory for definitional equality. Every primitive term former respects definitional equality. And it's similarly in lower observational type theory. We have congruence terms for all the term formers. So like pi1, for instance, there's a pi1 equals, which is sort of a different operation, the congruence operation that says if two pairs are equal, then their first components are equal and also the second components are equal. And then once we have those, we can do structural induction to prove that all terms respect equality of either sort. I've had to sort of decompose the term into all the different pieces that it's put together from, and then use these rules one at a time. In higher observational type theory, we're going to do this differently. We're going to assert a general congruence term. So for any term at all, so this here f, this term f is a term that involves a free variable x of type A. And we're going to say for any term f that involves a variable type A, and then an equality in type A, we're going to say that that term respects equality. So if I substitute the two sides of that identification into that term, then the resulting values are equal or are identified in the corresponding type. I'm going to ignore the fact that this type B might also depend on X. We'll come back to that later. The notation here is the app. So if you think of it as being like the application of a function to a path in Book HoTT, or the way we write it in any homotopy type theory. But this subscript is a term rather than a function with a free variable, and this notation here means that the variable x is bound in that term. So it's like when we write lambda x dot f, then x is bound in the term, the subterm f. And so what I was saying, instead of giving basic rules for each primitive term former and then putting them together by structural induction, we have this general congruence term. But then we do something very similar, we make it behave very similarly by giving it computation rules on the standard term formers. So if my term f is a pair, then this app here has to live in a pair type in something like A cross B. And so I'm going to just say, well, I could do app on each of the two components of that term that's in my subscript, and then I'll pair those up, and that's the value of my app. And similarly for projections, here app of pi1 is the same as pi1 of app. And all of these are well typed because I know that my previous rule, that it of A cross B is it of A cross it of B. So for instance, here in this one here, P, sorry, no, in this one here, P lives in id of A cross B. And so that's equal to id of A cross id of B. And so it makes sense to do app. No, sorry, I got it wrong. No, sorry. It's this is what I get for trying to do things off the spur of the moment. App of x, app of s of p lives in this product, id of a product, and which is the same as a product of ids, and so it makes sense to apply pi1 to it, and the same for the other ones. All right. Okay. Sorry about that. So again, we do this for all of the type forming all the kinds of types. We're going to have products and functions and sigmas and so on, but for now, this basic product type is enough to get the idea. So now, in addition, we want everything to be the same as itself. We want reflexivity terms. So we have this for definitional equality. We have this for lower observational type theory, and we're going to have it for higher observational type theory too. We call this refl of A. It exists for any type, and it has computation rules as well. So refl of a pair is a pair of refls. Refl of a projection is a projection of a refl, and so on, which are well typed for the same reason. And it's not a coincidence that this looks very similar to the rules for app, and we'll come back to the reason for that later. So I want to say a little bit more about app here. So you notice that we gave rules for app not only when what's down here is sort of an introduction form, but also when what's down here is an elimination form. So for ordinary sort of elimination rules like the induction principle for the natural numbers and so on, it only computes when the discriminant is a canonical form, like 0 or successor or something like that. So this is different. The app is computing on all terms at all, whatever they might be, even if they're not headed by a constructor. And so you might ask, what happens if what's down in the subscript of app is a redex? that we could also reduce on its own. But the way we define these rules, they're consistent with all of that. So if we have, say, pi1 of a pair down in there, so the rules for app would tell us first we can pull out the pi1, and then we can pull out the pair and get app of a pair. But now I have pi1 of a pair, and I can do the reduction here and just get the first component of that pair. And that would be exactly the same as what I would get by just reducing in the subscript here to get all the way over to there in one step. So regardless of how you do the computation, it's consistent. What we haven't specified is what happens with app when what's downstairs is a variable. It's sort of very clear what it should be, and so we give the rules for that. So if the variable is the bound variable, then what we've got basically is the identity function. So app of the identity function on P should just be the same input identification. It should act as the identity on identifications. And if the variable is different, then this is a constant function. And so we should just give reflexivity. App of a constant function on anything at all is reflexivity at the value it's constant on. So app, with these rules, an app is essentially never a normal form. It can always reduce. And you can think of it as sort of a higher dimensional explicit substitution. You can think about it and say, we have this term f that has a free variable x, and then I'm going to substitute this p for x, even though p is not an element of A, but it's an identification in A. And so this is kind of like in cubical type theory, right? If you have a path, you can think of it as a line that depends on an element of the type that depends on an interval variable, and then you can substitute it into any term and get a new term that again involves an interval variable. But now we're sort of incarnating this explicitly in the syntax rather than shuffling it off to interval variables. And then using this laws for variables and sort of and so on for individual terms, we get more general rules for the way app behaves on all sorts of things. So app on reflexivity always turns out to be a reflexivity. App is functorial definitionally, essentially sort of by induction over these terms that we might be looking at. And app of any constant term is reflexivity. So we sort of don't really need to assert these directly, but essentially they follow from the rules that we've given so far. So that's the basic structure of how we treat identity types and apps and reflexivity and so on. So now let's move on and talk about what the identities types look like at some other type formers, not just product types. All right, so let's start by talking about functions. So the obvious rule that you would pick for equality of functions is function extensionality. So you would think, oh, the identification between f and g should be for every input variable y, there should be an identification between f of y and g of y. But it turns out that this doesn't work very well for defining app on application. So right, if I have a function f in type BRC, and I have an input B in capital B, then I can apply them, right? So you could technically you would call this sort of app of FB, even though we sort of usually write it as just FB or f of B. But this is a term former. It's the elimination rule for the function type, and so we should be able to define app. We should be able to give a computation rule for app on this elimination, and it should live in. All right, so because this here lives in the type C, it should live in the identity type of C that we get by substituting these two elements of A into the application f of B. So this is, if we distribute this ordinary substitution, this is f at A applied to B at A on the one side, and the other side it's f at A prime applied to B at A prime. Okay, and we expect that the computation rule for this would compute it to something that involves app of f and app of b, because those are the inputs of the term. Right? Now, app of f lives in the identifications in the function type, and so if we use this function extensionality rule, then this would be, say, for every element of y and b, we would have an identification in C between f at a of y and f at a prime of y. And then there's also app of b, which is it of b at a and b at a prime. But the problem is that, so the only way to get an id of C is to apply app of f to something, but we can't get something like this that has two different inputs onto the functions on the two sides, at least not in a direct way. Because here, by definition, what this means, right, by our assumption appf lives in this function extensionality type, it has the same y here on both sides. So there are different ways you might try to solve this. I mean, in cubical type theory, in sort of recent Cartesian cubical type theories, we avoid this by putting in, we have diagonals of some sort so that we can sort of get some sort of square and then look at a diagonal of that square. But since we don't have diagonals, what we're going to do instead is we're going to do something which is similar to what happens in parametricity. If for those of you who might be familiar with that. If you're not familiar with that, it's okay, you don't need to be. So what we do is we say that an identification between functions is the assertion that whenever two elements of the input are equal, are identified, then their corresponding outputs under the functions are also identified. F of u is identified with g of v. And homotopically speaking, this is equivalent to what you would expect from ordinary function extensionality, because v and q together here form a singleton or a base path space, which is contractible. So once we have singleton contractibility, this should be equivalent to the naive sort of function extensionality. But it works much better for app on application, because if appf of p lives in this type here, then I can choose u and v to be these two things here that I wanted to get out as my outputs. And then app b of p is my path argument, my q. And now app on f of b can be computed to app on f of these two endpoints and then app on b. So making this choice allows us to compute app on application in a nice way. We also need to say what happens to app on a lambda abstraction, so the introduction rule for functions. Okay, so what we've got now is we're going to have, we want a lambda term belonging to a function type, which is going to appear in the subscript of an app, which means it's got to have an additional free variable x. So that means the body of the lambda, this term t, is going to be in a context that has two additional free variables, x and y. And now I want to form app on this, and it's got to live in this function identity type of the function type, which, as we said, is going to be pi of u and v and q of an identity between t with two different things substituted into it. Right, so we've got an a0 and a1 into x and also a u and v into y. So what can we compute this to? So the natural thing to do is to say that we want to app the term t on both p and q simultaneously. Right? We have a p, which is an identity between two elements of a, and we also have a q, which is an identity between two elements of b. And I'd like to say I'm going to sort of do a simultaneous higher dimensional substitution of p and q both separately into the term t. So there are different ways to do this. One way we might do it in a sort of the poor man's way would be to pair up p and q to be an identification in a product type, and then sort of uncurry t and apply it to an element of that product type. But it's cleaner to actually introduce a multivariable form of app. So we're going to say, we're still ignoring possible type dependency. We're just going to say, if I have a term t here, which depends on an arbitrary finite number of variables, free variables, then I can bind all of them and apply that term to the same number of identifications in the corresponding types and get an identification in the output type. And then app on a lambda is going to be computed to this double app with two free variables. And then, of course, we have to give rules for how to deal with computing with a multivariable app. So for instance, if I want to do app of, say, x1 and x2 on lambda, right, then that's going to compute to something or other involving app of x1 and x2 and y. Right, so every time we do this, the number of bound variables increases by increments by 1. Right. And sort of all the other same rules for products and so on will apply, don't change the number of bound variables, so they apply just as well for multivariable app. And we also have rules for the variables. Remember I said for ordinary app, we had if the variable, if the term down here was the variable being bound, then app computed to the path, the identification. And similarly, for multivariable app, if the variable is one of those that's being bound, then we compute it to the corresponding identification that matches that has exactly the right type. And if we have a variable that's not any of those ones, that's not in any of the bound variables, then we compute it to reflexivity. And now once we have this multivariable app, you can say, well, there should also be a version when n equals 0. And what happens when n equals 0? Well, when we have n equals 0, we don't have any bound variables, and we don't have any identifications as inputs. All we have is a term, and this is supposed to be in id A of AA. And so this is just reflexivity. So essentially, we define or identify reflexivity with the zero array app. And this explains why all the computation rules for reflexivity look just like the rules for app, because they are actually all special cases of those same rules, just instantiated at n equals 0. Okay. So now we have the basic rules for computing with app and identity types of pairs and function types and multivariable apps and reflexivity, and it fits together pretty nicely. But we haven't dealt with type dependency, and we haven't dealt with the universe, Univalence. Okay, so I'm going to talk about the universe first, actually, Univalence, and then we'll see that actually solves the problem of type dependency in a clean and nice way. So we'd like Univalence to hold by definition. Just like function extensionality, we wanted it to hold by definition. So id of the universe should consist of equivalences. But what kind of equivalence? Right, so there are lots of different kinds of equivalences. You can read about them in chapter 4 of the HoTT book. There are maps with contractible fibers, which was Blavatsky's original definition. There are half-adjoint equivalences or bi-invertible maps. We could just choose one of these. And in cubical type theory, when they define glue types, you choose one of them. I think you choose Blavatsky's notion of equivalence, usually at least. But I have a problem with choosing any of them because none of them feel very canonical. Why would you choose one instead of the other one to incarnate basically in the syntax of your type theory? They're also all kind of annoying because none of them are definitionally symmetric in A and B. That's not really necessary because we don't have a definitional kind of reversal in our theory, but it's kind of icky. And some of them are kind of hard to motivate without already knowing that you want to do homotopy theory. Right, because half-adjoint equivalence is bi-invertible maps, for instance. Right, the reason you can't use just an ordinary quasi-inverse, where you have maps in both directions and homotopies and nothing more, is the reason for that is essentially homotopical. I mean, you can write down a proof that it would be inconsistent to do univalence that way, but sort of why is it true? Well, because of homotopy theory. That's the way I feel anyway. All right, so that's sort of a problem that we encounter when we try to say what do we want by definitional univalence. And in fact, it's actually kind of confusing what we should mean by definitional univalence anyway. There's in the book there's sort of 3 properties given of what a good notion of equivalence should be, and the properties were given there in terms of the property of a function being an equivalence, but we can restate them in terms of a type of equivalences. So whatever we mean by a type of equivalences, it should be a subtype of the function type, and it should be logically equivalent to this naive type of quasi-invertible maps. If you have a quasi-invertible map, you should be able to make it into an equivalence. An equivalence should have an underlying quasi-invertible map, and a function should be able to be made in equivalence in at most one way, up to homotopy. And for any notion of equivalence, you can state univalence using this notion of equivalence that satisfies these properties, and you'll get an equivalent axiom, regardless of which notion of equivalence you choose. So this is sort of the Book HoTT up to equivalence notion of univalence. But the weird thing is, once you state univalence, once univalence is true, then the identity type of the universe also satisfies these 3 properties. because these properties are invariant under equivalence of what this type of equiv is. So in that sense, maybe univalence always holds by definition, because it's right, as soon as it holds, you can define equivalent to be id-u, and then it holds by definition because you've defined the notion of equivalence to make it hold by definition. I mean, this is obviously sort of a cop-out. This isn't what we mean by saying univalence holds definitionally, but what do we really mean by saying that univalence holds definitionally? So I would argue that what we really want when we say univalence holds definitionally is that univalence holds in a way that remembers the underlying maps, the underlying functions, at least. Because those are things that it's useful to remember. So suppose we have some notion of equivalence that's written as a sum over a pair of maps f and g, and then some other stuff. So this is like this cloud is like the half adjoint equivalence, or by invertible map, the extra data there that makes it a coherent notion of equivalence. And then to say that univalence holds definitionally, we should be able to make equivalences into identifications in the universe, and then extract out an equivalence again. And I'm calling these things up and down. So it's like I given an equivalence, I promote it into an identification in the universe, and then I can sort of demote or extract out an equivalence. And I'd like that, I'm going to write these as postfix. And then I'd like to be able to say that if I take an equivalence and I promote it and demote it again, I remembered the same underlying functions definitionally. Maybe the other stuff here got fudged or messed with, but the same functions we should be able to extract. You could also ask to be able to extract higher homotopies, but this is sort of the base level 1 notion of what we would like to have when univalence holds definitionally. And as I mentioned at the beginning, even this isn't true for the current versions of cubical type theories. You can't even extract the underlying function definitionally. It gets composed with some non-trivial transport. So the good notion of equivalence that we're going to use is what I like to call the type of one-to-one correspondences. So this appears in an exercise in chapter 4 in the HoTT book as proving that this is a good notion of equivalence. So a one-to-one correspondence is, well, it's a correspondence. That's what I like to call a type dependent on 2 types. So this is a family of types dependent on an element of A and an element of B. Sometimes this is called a relation, but I would rather not call it a relation unless it consists of propositions. So in general, it's a correspondence. Sometimes correspondence is used to mean the same thing as span by geometers or category theorists. And so that's nice because this is semantically the same as a span. It's just in the same way that a fibration is the same as a type family. So a one-to-one correspondence is a correspondence such that each element of A or B has exactly one correspondent on the other side. So every element of A, there's exactly one element of B that corresponds to it. In other words, the type of B's that correspond to it is contractible. And similarly for B, the type of A's that correspond to it is contractible. So I think this is fairly easy to motivate even without homotopy theory, because it's just really a propositions as types version of sort of a bijective relation. Basically, you sort of take everything and make it into a type. It is definitionally symmetric. And this is sort of one of the reasons that I think it was Peter Lumsden who first proposed this because, as a version that could be definitionally symmetric. It has a disadvantage that it's in a larger universe than A and B. But the identity type of the universe is also in a larger universe than A and B. So if we want to define id-u to be some notion of equivalence, that really we shouldn't really be an objection. And it also turns out to work really well, as we will see in the next 15 minutes. So first of all, let me say a bit about how it corresponds to sort of more naive notions of equivalence consisting of functions. So if I have a one-to-one correspondence, R, then in particular, I have centers of contraction for each of these contractible types. In other words, for every element of A, I have a specified element of B that's related to it. And in particular, that gives me a map from A to B. And similarly, on the other side, for every element of B, I have a specified element of A that's related to it, and that gives me a map from B to A. So that gives me the functions, and then the rest of the data you can extract a proof that these are an equivalence. Conversely, if I have an equivalence, then I define a relation between A and B by saying that A is related to B if B is equal to f of A. I have to make a choice there. It's sort of not symmetric there because the notion of equivalence is not symmetric. But once I make that choice, then I can prove that this is in fact a one-to-one correspondence. And moreover, I can choose the centers of contraction to be these given by these two functions f and g that I specified when saying that I have an equivalence. And therefore, if I take an equivalence and I make it into a one-to-one correspondence, and then I extract an equivalence again, I get out the same functions that I put in up definitionally. So this is a good notion of equivalence to take as our, essentially by definition, identifications in the universe, and hope to be, so that we'll get a definitional kind of univalence. You can also give a fancier definition of this one-to-one correspondence that actually remembers the homotopies as well, but I don't want to get into that right now. So what are the actual rules that we give? You might have expected me to say that we're going to define id-u to be the type of one-to-one correspondences. And we're not actually going to do that. To be honest, this is one of the places where the details are not completely worked out, and they might end up changing a little bit. But at the moment, this is what I believe the best way to do things is. Instead of saying that id-u is by definition equal to one-to-one correspondences, we're going to give it promotion and demotion rules relating it to the type of one-to-one correspondences. So we're going to say any one-to-one correspondence can be made into an identification in the universe, and any identification in the universe from any one of those we can extract a one-to-one correspondence, which is definitionally the same as the one I put in, if it was the one that I put in. And that's enough to give definitional univalence, because we've already seen that if I take an equivalence and make it into a one-to-one correspondence, and then I take that same one-to-one correspondence and extract an equivalence, I get the same underlying functions. The reason for not having this actually be definitional, I will explain those later. So if I have time at the end of today, I'll give some philosophical reason, and then in the next week and the week after, I'll give some syntactic and semantic reasons for this. You can think of this as kind of like a co-inductive type that has exactly one destructor. So a co-inductive, this is the destructor of the co-inductive type. And then we essentially, right, if I have a co-inductive type with one non-recursive destructor, then the co-iterator would basically say, in order to define an element of it, I just give an element, I give the result of that destructor. And then the computation rule is that the destructor computes on the co-recursor, and there's no eta rule. You can't have an eta rule in general for a co-inductive type. So from a computational standpoint, this is a sensible thing, at least, even if it's not what we might expect exactly. So that's our form of definitional univalence.
Mike, I'm going to interrupt you before you go on. There's a question in the chat that might be relevant. Egbert asks, is it not a problem that you don't have sigma or pi or even dependent types in general? Are you just, and I'm adding, are you just kind of sweeping that under the rug for the moment and you'll fill it in later?
Yes. I'm sweeping that under the rug for the moment, and I will fill it in later. And in fact, I'm going to fill it in very soon. So we have sigmas and pi's in the theory. I've been using them all the time. I haven't specified how id computes on sigmas and pi's. And I'm going to do that in a few slides. So hopefully that answers the question.
I think so. Yes.
Okay, great. So let's say what we extract.
There's another question coming from somebody named John Hopkins.
Okay.
I think that's a pseudonym for Emily's group. Could you say more why core, capital C-O-R-R, is a definitional retract of id, but not a definitional iso? Something about eta and co-inductive types that I don't.
You mean, yeah. So you mean why we don't ask for the other rule?
Yeah, I think that's right.
Yeah. So I'm glad that you phrased the question as, could you say more about? Because the answer is no. Not right now.
Okay.
I'm sorry. I realize this is unsatisfying, but I'm going to ask you to hold that in abeyance and just take this as an assumption. I'm going to explain later on why we don't. I'm going to explain tomorrow and next week and the week after, essentially why we don't have that.
Okay, we'll give you that grain of salt.
Thank you. For now, you can sort of imagine that we do have this rule. Really, nothing that I'm going to say the rest of today is going to depend on not having this rule. So you might as well assume that we do, and then next week I'll explain why we don't. or and the week and the week after. Any other questions?
Yep, here's one from Jason Gross. Do we get to prove J for is
Yes.
in this theory?
Yes, in a moment.
Moment, okay.
In a moment.
Okay, so that
All
clears
right.
that for the moment.
Yes. All right. So let's look at what this sort of definitional univalence gives us. Okay, so first of all, every element of the universe has a reflexivity term. And if I demote that to a one-to-one correspondence, I get a specified one-to-one correspondence from every type to itself. Okay, so in particular, there's an underlying correspondence from every type to itself. And what should that be? Well, clearly it should be the identity type of that type. Okay, so pi 1, but this pi 1 here means that I'm projecting out to this component of a one-to-one correspondence, the actual correspondence itself. So pi 1 of the demoted REFL of A is the identity type of A. And I like to kind of regard this as a definition of the identity type, but I mean, of course, you have to already have the identity type of the universe in order to make sense of it. Now, we also need, we also have the other components of REFL of A, which say that the identity type is a one-to-one correspondence. That is what we call singleton contractibility, right? It says for every element of A, the type of B's that are identified with it is contractible. And similarly on the other side, right? And so this gives us some homotopical operations. It gives us composition operations, for instance. If we have, right, if I have an identity between A and X and between A and Y, then that gives me two different elements of this type over here that's contractible, and therefore those two elements are equal, and in particular their first components are equal, and so that gives me a way of sort of composing the inverse of P with Q to get an identity between X and Y. So there are different ways of slicing and dicing this and sort of reversing things and so on, but I just want to say that roughly speaking, singleton contractibility gives us composition operations of some sort or another. From A equals X and A equals Y, we get X equals Y. We also, right, we also want to compute this on everything, right? So REFL computes on all terms, right? REFL of a pair is a pair of REFLs, REFL of a projection is a projection of REFLs, and so on. So REFL of a product type, right, which is a term in the universe, should be computed using REFL of A and REFL of B, right? And so the first component of that computation is just the computation of the identity type, because the first component of REFL, the demotion of REFL, is just the identity type. And so the rule we gave for computing id of A cross B to id of A cross id of B is part of the rule for computing REFL of A cross B. The rest of the rules for computing REFL of A cross B tells us how to compute singleton contractibility in terms of the components, right? It basically says, given that I know why the singletons in A are contractible and why the singletons in B are contractible, then I can construct proofs that the singletons in A cross B are contractible. And so in particular, that tells me how to compose paths in a product type A cross B in terms of how to compose paths in A and in B. We also have app, which is we can apply to terms valued in U. So here, for instance, let's just look at the one variable version. If I have a term in U, which depends on a free variable in A, and then I have an identification in A, I can apply app to it, and I get an identification in the universe. And then I demote that to a one-to-one correspondence and pick out its correspondence. I get a correspondence between B of X and B of Y. And this is, we essentially take this as the definition of a dependent identity type. Right? So in Book HoTT, there are different ways to define a dependent identity type of a fibration or a dependent type. But the idea is we have sort of a path P between X and Y downstairs, and we have a U and a V upstairs living over U living in B of X and V living in B of Y. And then there's a type of sort of paths for U to V that live over P. Which is not the same as paths in the fiber over here or paths in the fiber over here, although it can be related to them by a transport operation. In cubical type theory, we have a different way of defining these dependent path types. In higher observational type theory, we define the dependent path type, or the heterogeneous path type, which I'm writing like this with a bound variable in the subscript of the id, is essentially this. We take B, regard it as a term in the universe. We do app to it to get an equality in the universe. We demote it to a one-to-one correspondence, and then we apply it to these points. Does that make sense? And of course, we can do this for the multivariable app as well. The rules for computing with dependent identity types give us, the rules for computing with app essentially tell us that we have to be able to compute with these dependent identity types, right? App is supposed to compute on all terms. So we have to have a rule for app on, say, B cross C. And in the first component, that tells us how to compute id of B cross C. Then it also tells us how to compute the other pieces. And we also have these same functoriality rules. I'm running a little bit low on time, so I'm going to skip discussing all of those. The other components of app on a term valued in the universe are singleton contractibilities for dependent identity types. Right? So they're basically saying this dependent identity type is a one-to-one correspondence between the type over X and the type over Y. And so what that means is if I have an element of B of X, then there's exactly one element of B of Y that corresponds to it. And the element of B of Y that corresponds to it is essentially a transport of U across that identification path to live in B of Y. And then there's all that correspondence, that witness that it corresponds is a dependent path or dependent identification living over P. So I'm given a U over there, and then I'm basically saying I can transport it along there and get a path that's sort of lifted along that living in the identifications. And there are dependent identifications. And then there are computation rules for this on path type, on particular constructors like B cross C and so on, like we did for everything else. These rules are ones of the ones that I said we'd like to get the whole definitionally. Okay, so now to answer those important questions in the last minute here, right? Path induction, elimination J, the J rule comes from singleton contractibility and transport, just like in cubical type theory. So if we have the sort of thing we'd like to eliminate into for J, and we have a point over here that we'd like to apply it to. So this is the version over REFL, and we have a path or an identification we'd like to transport across. Then singleton contractibility says if I pair up this identification with B, that lives in the same type as if I pair up A with reflexivity. It lives in this sigma type, and so singleton contractibility says that those two are identified. And then my C, my motive here, can be curried to be a type dependent on this sigma type. And then I just transport across this identification. I transport my U, which lives over this guy, to something which lives over this guy in my C twiddle of A. And that is precisely the type that I wanted to get. So this is the same thing we do in cubical type theory. We get cubical type theory, we get these things for a different reason, but this is essentially the same proof to get J from these things. And for essentially the same reasons, we only get the beta rule for this so typally rather than definitionally. So if you apply this thing to REFL, you don't get back the U definitionally. And then to answer the question about sigmas and pi's, the computation rule for id on sigma is a sigma using a dependent identification here, and the same for pi's. Right, so what does it mean for two dependent pairs to be equal? We say the first components are equal, and then we say the second components are equal depending on or heterogeneously over that identification of the first components. And there's a similar rule for the pi types. And so the sigmas are basically just like the product types. The pi types are basically just like the arrow types, where we take the 2 points and an identification between them. But then we use dependent identities at the last point. And now we have those so that we can use them. So that's the univalence essentially solves all of these problems for us when we give a definitional univalence like this. Okay. Yeah, and there's a multivariable app in it. Okay, so I think that's a good place to stop.
Okay, thanks, Mike. We're going to thank you silently here in the video. Please send your questions to me in the chat, and then I will read them out. So here's the first one already. It's from John Sterling, I guess, and it says, is it perfectly consistent and validated in the main models to add regularity to it is, sorry, this is not the question part yet. It is perfectly consistent and validated in the main models to add regularity to cubical type theory. Thus, the lack of beta rule is not essential and can easily be repaired. Is there any semantic obstacle to having a beta rule for J in HoTT, that's the capital O,
Yeah.
or are you omitting it for syntactic reasons? Do you want me to repeat the question?
No, no.
Got it? Okay.
I think I got it. So the short answer is that we have not fully investigated that question yet. And so I don't really have a definite answer. It's in the models, in the main models that I'm interested, or sorry, in the higher topos models anyway, I'm pretty sure that one can construct a J which does satisfy definitional beta. But it's not the same J that you construct from transport and singleton elimination this way. Yeah. So it's in that sense, it's consistent and validated in those models to add a primitive J operation, which does have a definitional beta, which might be the same thing that you're saying you can do in cubical type theory. I do not know of a way in any model. I do not yet know of a way to construct a model in which this J that you construct from transport and singleton contractibility satisfies definitional beta, but I also don't know that it's impossible.
Okay, is that the answer?
Yeah.
Okay, you ready for the next question?
Yes.
The next question is from Andy Pitts. Can you do a swan-like correction? I assume that's not like a swan dive. That's
Yeah.
an Andrew Swan-like correction to your id type to get an identity type with a definitional beta rule. I think that's a similar issue.
Probably. So again, there's a limit to what we've done. We've worked out so far. Right? We're trying to get so far. To start with, we're trying to get a theory that works, and then we can try to improve it. My understanding of the precise specification or the construction of the swan identity type is that it uses the interval in cubical type theory. So I don't think we could do exactly that. But it seems not unreasonable to me that we could do something similar, and that gets into the area of inductive types and indexed inductive families and so on, which is another part of the theory that we haven't completely nailed down yet. But I have hope that something like that could also be done. And I'm done.
Okay. Good. So now I'm asking Jonas to please unmute Torsten, who wants to add something. And I think he will let him speak for himself since he's one of the authors here. Yep.
Yeah. I just wanted to add something more along the line what just Mike said. So once we have inductive families, and I think we've got some ideas how to do this, then you can actually write down the inductive family, defining equality as an inductive family. I mean, which is the idea. And for this one, the beta rule, the J beta rule should hold definitionally. So, yeah.
Right, which is not exactly the same, if I understand correctly, as the swan identity type in cubical type theory, but it's something that has it should be something that has a definition.
So there's always a way to recover. I think there's always a way to recover an identity type which is equivalent the type we built into the theory, which satisfies the J beta rule, which is regular, but which may then obviously on the other hand loses some other definitional equalities. Yeah.
Right. It'll behave more like the Book HoTT identity type.
Yeah.
Okay, maybe this is related. This is a question coming from, again, John Hopkins. Do the definitional equalities of the identity types give you definitional higher structural identity principles? And then here's a follow-up. If yes, philosophically, I always thought it was cool that these were theorems because Markov identity types plus univalence somehow always give the right answer. Can you comment on that?
Yes. So structure identity principles, meaning things like equalities. The inequality of groups is a group isomorphism, and so on, I assume is what he means. Yes. So for instance, if you define, say, the type of groups to be, say, something like this, right? And then if I have an identification in the type of groups between G, M something and sort of H, I don't know, something, right? Then the rule for identifications in a sigma type that I sort of went over real quickly here tells me that this computes to an identification of the first components here, in id of U of the underlying types G and H, and then an id of the second components, right? So this is an id in the type. So this is dependent over this of the type sort of in the type X to X to X, which is dependent on X of sort of M and M prime, and then identifications of the other pieces as well. Maybe this should be the type of sets or something like that, whatever you want to do it, if you want set groups, right? And then so this here, this piece is going to be an one-to-one correspondence. Basically, you're going to be able to demote it to a one-to-one correspondence, and then this here will turn out to say that these two operations are equal relative to that correspondence, right? So you'll have an R. The piece of R, this one-to-one correspondence here is going to be involve a correspondence R from G to H to U, which basically tells you when an element of G and an element of H correspond to each other. And then this identification over here is going to say whenever I have, say, two elements of G and two elements of H, and the first ones are G and H correspond to each other, right? So they're and G prime and H prime correspond to each other. Then M of G prime corresponds to M of H prime. So this is essentially saying, if I say R of GH, you should think of that as essentially saying I have some group isomorphism such that phi of G is equal to H. And so this was how we defined the one-to-one correspondence coming from an equivalence. And so basically this is saying if I have two elements of G and I define H, G, and G prime, and I define H and H prime to be their images under this isomorphism, H prime is phi of G prime, then phi of GG prime is equal to H prime. So phi is a group isomorphism. So in that sense, this sort of structure identity principle that identifications in the type of groups are group isomorphisms comes out of these computation rules for identity types in a certain sense, right? It's not literally the type of group isomorphisms that you would write down involving a function and so on, but it involves this identity type of the universe, and which demotes to a one-to-one correspondence, and then this notion of preserving the operation that's relative to that correspondence. The last part of the question, I think you were saying that you would find it less satisfactory for a structure identity principle to be definitional rather than to be a theorem, or something like that.
We don't remember that part. It just says that
would find it.
It's cool that you always get the right thing.
Yeah, I mean, I think it's cool that you always get the right thing too.
Okay,
I guess I mean, it's nice that it comes automatically from the J rule in Book HoTT, and that's sort of part of what I said I like about Book HoTT at the beginning, that everything comes automatically from that. And I find it about equally satisfying that everything comes from the computational rules for identity types here. I find that also philosophically satisfying.
Yep. Okay, well, let's move, because we have a whole bunch of questions here that
All right.
I can get to, and I'm going to try to kind of take them in order. So there was a question during the talk from Jason Gross. Are the two projections of the second projection of Raffle A down judgmentally equal? Oh, maybe that's a quickie.
No.
Okay, that's the answer to that. Then there's a question from, unless you want to say something more about that, Mike, sorry.
They're not definitionally equal, and moreover, their centers of contraction are not definitionally the identity. So that's a failure of regularity also.
Okay, then there's a question from Thomas Streicher. How can every type in a universe have an associated id type, since the universe contains elements not coming from syntax? That's the question.
Not quite sure how to answer that. So today I was only talking about syntax.
Okay, maybe that's
so I was describing the syntax of a type theory today, and so I only need to give rules for how to deal with syntax.
Okay, but then I can flesh out the question a little bit more. Don't you want to interpret this system into other settings like infinity toposes, where
yes,
not it comes from syntax?
Absolutely. So
maybe that's the question.
Yeah, so that the full answer to that question will come 2 weeks from now, when I talk about modeling univalent universes. But the short answer is that when we construct a model of syntax, we incorporate the identity types into the elements of the universe. So essentially, an element of the universe is a type together with all of its identity types.
Okay. So here's another question. You mentioned that both first and second gen HoTT suffered from the fact that many equalities are not definitional. Does HoTT solve this problem? Since path transport is canonically defined, it seems that it should, and moreover, that many proofs in the HoTT book could be significantly simplified. That's from Nicholas Schmidt.
Yes. Not all the definitional laws you would like are going to hold, but many of them do, and many of the same laws that hold in cubical type theory hold. So I mentioned a few of these. Let's see, right? So when I was talking about this here, so you have these law, right? In higher observational type theory, this law is a definitional equality. This law is not a definitional equality because we changed what appears over here, but there's this other thing which is a definitional equality. This law here is a retraction. Remember, right? So we were saying this thing on the right is a retract of the thing on the left. So we don't have definitional. We don't have all the definitional laws we might want here, but all of these laws here are definitional. So the same ones that you get in cubical type theory for functoriality and transport and so on. And I mentioned some of these at some point during the talk. So the functorial laws for app, for instance. This one here comes from sort of basically structural induction over the structure of F and G, using the fact that we can compute app on all of these. Transport, with the way we got transport, was from singleton contractibility of the dependent identity types. And because we compute app on all terms, in particular, we're computing app on B cross C, that tells us how to compute transport on B cross C into a pair of transports. There's various things like that. So yeah, a lot of those rules do end up becoming definitional. And I mean, you can hope that maybe some things in the HoTT book would become easier. Some of the things like the characterization of identity types of various iterated sigma types ought to be a little bit more straightforward, but we haven't really tried to figure out exactly how much things simplify yet.
Okay, so we are trying to unmute Hugo Herberlin, and we're not going to make him type out this whole question. He has something he wants to add with regard to parametricity. Jonas, can you unmute Hugo?
Yes.
There we are. Yeah, we can hear you.
Mm-hmm. Oh, he's muted again.
Oh, you're muted again, Hugo. There. Okay, good.
Yes, just to say, I'm glad to see that you take this into your hand, Mike. So I think it's when was the paper from Thorsten on the Ambrouche in 14?
Yeah, something like that.
So on the for me, it has been obvious that this definition they use of equivalence was the right one with very good properties. So I think it's very good that it comes mainstream. So as you may know, I vaguely, so part-time, investigated how to rephrase a form of cubical type theory. So not the one you call second generation, but one what that should be called third generation in your terminology also, based on this definition. And so what I had in mind is a syntactic model based on iterated, what I call iterated delimited parametricity. Which is the same as the parametricity translation with bridge, but you replace the bridge, you extend the bridge, you add more structure, because the definition you gave, OnetoOne correspondence, you call it, it's basically bridge extended with structure, and how this iterated delimited parametricity translation would provide a cubical type theory with the same kind of definitional rule you present. And but it's something I work in just a few weeks a year, so every year. So it's good that someone explored this direction. So I think you don't have in mind a syntactic model. I mean, in the sense of translation to ETT, sorry, for instance. You more have in mind, I guess, a model in infinite topos, for instance. But this is a very interesting direction. I think this is really the next HoTT indeed. So just a comment.
Yep.
Thank you.
Okay, Mike. I don't know if you need to reply. We have a long list of other questions here. Maybe we can get to some of those.
Yeah.
But thank you, Hugo, for that endorsement. I guess. Mike, is that about right?
Yeah. I don't know if I have any reply.
Okay, good. Let's see. I think the next one is Danny Greitzer at Chalmers on behalf of a viewing party there. I guess they're already celebrating. Can you comment on the relation between this system and the Reedy fibrant model construction over two parallel marked arrows? It's kind of sophisticated.
Models for two parallel marked arrows. Okay. I think I know what you mean.
Okay. Go for it.
So if you have So I think by redefibrant model construction, I think you mean if I have a model of type theory, then I can build another model in the type of in the category of diagrams that look like this, where we require sort of this map from A1 to A0 cross 0 to be a fibration. So that's sort of the readiness. And we also require the two projections to be equivalences. So that's the markedness. Right. So you can, in that case, so you can think of A1 as sort of a specified identity type of A0, because it's dependent on two copies of A0, and each of the two singletons are contractible. So I would say the relation is that sort of this construction is maybe the first step in trying to build a model of higher observational type theory from some category or other sort of model of type theory or homotopy theory or model category over here. It's not enough for two reasons, or for even three reasons. So one reason it's not enough is that A1 doesn't have an identity type. So every type has to have an identity type, including A1. So really you need an additional, you need some extra stuff that lives above here. So you need to actually extend it to diagrams on some higher cube category, essentially. The other reason is that you also need, the second reason is you also need reflexivity. And so you need not just downward going arrows, but also an upward going arrow. And so essentially what you need is a whole cube category. And as we'll see next week, it seems that you also even need the symmetry operations as well that aren't obvious here. So because of all that, I don't know of a way to start with an arbitrary model of type theory and make a model of higher observational type theory this way, because you sort of need a bunch of strictness here. But this is the idea of how to model it in a higher topos. If you start from a nice Quillen model category here, then you can do this construction and in fact use a reedy model structure of the generalized sort.
Okay, we have a lot of questions remaining. I'm just going to kind of pick and choose some that seem to be the most general interest, and the other ones I'm going to save the chat. I'm going to forward them to Mike, and perhaps he can answer them on the hot Zulip. And
Yeah.
Here's a good one from Reed that I think other people are asking themselves too. Reed Barton asks, what about higher inductive types? Are you going to talk about that later? Or is there something else that you could say now?
Well, higher inductive types are work in progress, is the short answer. There are difficulties with higher inductive types in the absence of diagonals, as people who are familiar with cubical type theory may know. We're hopeful that we'll find a way to work them out and come up with a notion of higher inductive types that will work. I think that's about all that I can say now.
Yep, okay, that's fine. That was also a question from somebody else, Ben Longston. Torsten wanted to get another crack at answering Thomas. Do you still want to do that, Torsten, or do you want to pass? If you want to, you can try to unmute yourself. I think you're still permitted. Pass, okay. And then let's go on to Josh Chen. Do you already have some indication that this approach to identity types banishes enough of the higher coherence obstructions to defining semi-simplicial types, or is this still some ways away?
I don't expect that this is going to make any difference one way or the other to that problem.
Okay. Good. Okay, maybe the other stuff I'm going to put in the Zulip, because we only have a couple minutes left, and the Topos colloquium by Martina Scardo is starting in a few minutes. Right. And I'm sure people want to go to that, and I don't want to hold them up from that. So folks, those who remain, let's thank Mike again for this great talk, and we look forward to next week.